In the previous videos, we have looked at ODE systems and matrix exponentials. Now we're going to go into a new topic, the Laplace transform. And the first step into that is motivating why we want to go into the Laplace transform at all. Well, let's look at what we can and cannot solve yet. If a system is linear homogeneous, now we can solve it in two ways. We can look at its characteristic polynomial, then compute lambda, the solutions of the characteristic polynomial, and we know how to build a solution based on the eigenvalues that we have found, the values of lambda that we have found. Or we can solve it as a first-order ODE system, creating the matrix of coefficients and solving as a matrix exponential. But what if it's non-homogeneous? Well, as a general statement, the solution of a non-homogeneous problem takes the form of the general solution, that is the solution of the homogeneous problem associated to our non-homogeneous problem, plus a term that we call particular solution. That is a term that fits into our equation just so to take care of the non-homogeneous part. For the equation that I randomly wrote, the particular solution can be found quite straightforwardly, because adding a constant to our solution, the constant 1, fits nicely. But if we have something more complicated at the right-hand side, for example, the sine of 2x, that is called a forcing term, then we need some more powerful tools. In the same way as non-homogeneous problems are usually not possible to be solved yet, non-constant coefficients ODEs are not solved yet. With the tools that we have, we're not able to do that. For this reason, we will introduce now the Laplace transform. It's going to take a little bit before it's clear why the Laplace transform can help us for solving ODEs. So bear with me. Let's look into the Laplace transform. In the previous video, we have seen how we have still quite some classes of problems that we cannot solve. And I have claimed that the Laplace transform is what is going to solve all our problems. So let's start at looking at what a transform is. So let's do a step back and look at what a function is. A function takes a value that can be real or complex and returns a value that can itself be real or complex. If we want to write it down, we can write it as this formulation. We have R being the real line, and we have F going from R to R, or a subsection of R. A transform that has many other names can also be called a function operator, sometimes operator for short. Instead of taking a value and returning a value, takes a function and returns a function. So we can write it in this coarse way. It's something that goes from the big set of functions into the big set of functions again. The most common form for a transform is this integral. So it takes f of t, small f of t, as an input and returns something that has an integral over t, and the integral itself is k times f. And k depends on s and t, and f depends only on t. K is called integration kernel. Then the return of this thing is a function of s. You can think of it as s being a parameter in our integral. We can write it explicitly by writing s in our formula, or dropping the dependency of t, since t is a dummy variable. The Laplace transform itself has an integration kernel that is an exponential of minus s times t. Sometimes I write it with the curly L to remember ourselves that is specifically the Laplace transform. When does the Laplace transform exist? It exists if small f of t satisfies two requirements. It needs to be piecewise continuous between 0 and a for any a bigger than 0. This is a ploy to never use the infinity. But for any interval from 0 to a, then a is piecewise continuous on that interval. And f is of exponential order. This means that as t tends to infinity, f of t, the absolute value of it, can be bounded by k being a real constant times the exponential of ct. Small t is the same as the one inside the function, and c, k, and big T are chosen real, such that this formula here holds for all values of small t bigger than big T. Then, if these two requirements on ft are satisfied, then the Laplace transform exists for all s bigger than small c that we have introduced for the exponential order. Why do we need these conditions? Well, it's just to check that the integral between 0 and infinity of ft times the exponential of minus st actually exists and is well defined. Let's look at some existence examples. For example, if you take f of t being the exponential of t squared, there is no k, c, and t such that f of t can be bounded by an exponential of ct. That means that the integral between 0 and infinity of our function times the exponential of minus st is infinity for every choice of s. That means that our Laplace transform of f of t is not well defined. We should not be using Laplace transform in this context. But let's look at this more complicated function, sine of x times exponential of 5t. Well, we can trivially bound this by the exponential of 5t for any t positive, because sine of x is between minus 1 and 1. That means that our exponential, our Laplace transform, is less than infinity and well defined for every s bigger than 5. So we can use Laplace transform in this context.